Hey guys. Okay, so let's get back into chapter 8, right where we left off. I actually think we went over this page already, but just to quickly review, we had done our sampling experiment to come up with two different sampling distribution of the means. We had looked at our population distribution, which was all of your ages, which we saw was very right skewed. Then we took a number of samples of size 4, calculated the mean for each one. We saw that it was still, fairly skewed, but definitely more tightly clustered. And then we did another set of samples with a trial size of 10. And at this point, we see that it's getting closer to being bell-shaped, still a little bit skewed, definitely more tightly clustered. And we also noticed that all of the distributions were centered kind of around the same value, which is the mean of the population, which is 28.125. So we had already kind of summarized all of this. So let's go on to the next page, which would be, whatever page number this is, page 8. Okay. So the impact of the sample size on the sampling variability. Okay. So as we can see right here, the sample means cluster more closely around the population mean as the sample size increases. In other words, the larger the sample size, the smaller the sampling error tends to be when we're trying to estimate a population mean by using a sample mean. So therefore, if I take a bigger sample, I am more likely to get closer to the true population mean. Okay, because that's what we want to do, is be able to go take a sample and from that sample estimate what the true population mean is. Okay, and the reason we care about this is because sample means, or proportions, which we will also talk about, will vary. Okay, samples vary, therefore the sample means will vary. We saw that every time we took a sample, we usually got a different value for the sample mean. Okay, there is always going to be some error in sample statistics, and usually when people like Gallup or Pew or whoever go out to take a sample to learn something, they usually only get one chance to sample. Okay, and you know that there's going to be some error in that sample, and you know that the mean of that one sample will not necessarily exactly represent the true population mean. So what we want to know is, well, how much might that vary? How far might that sample mean be off from the true population parameter? Okay. All right, I'm going to scooch on to the next page. All right, so the mean and the standard deviation of the sampling distribution of the sample means. Okay. So from our sampling experiments that we just did, we saw that the mean of the means, okay, in other words, the mean of these means and the mean of these means, was approximately the same for both sample sizes. And we saw that those means were approximately equal to the population mean. Okay. So here is a statement about the mean of the sample means. For samples of size n, the mean of the variable x bar, the sample means, equals the mean of the variable under consideration. Okay? In other words, for any sample size, the mean of all possible sample means equals the population mean. And if we were to write this out in symbols, we would say this: mu sub x bar is equal to mu. Okay? Where mu sub x bar is the mean of all the sample means, and mu is the true population mean. Okay? So from our sampling experiment, I told you before we started that the true population mean of all of your ages, so 32 students, I calculated the mean age, was 28.125 years. Okay. So for the first experiment, the sample size of 4, theoretically then, the mean of the sample means should equal that exact value. It should equal 28.125. So now if you guys remember, you took all those sample means that you had each calculated and you wrote them down on the data sheets. So I brought those data sheets home, I typed them all in, and I calculated the actual mean of your sample means, and we ended up with 28.746 years. Okay? So actually very close to what was predicted. Okay? Same thing for the sample size of 10. Theoretically, the mean of all of your sample means should equal the mean of the population, 28.125. From the actual results, when I took all your means, typed them in, calculated the experimental mean, I got 28.697. Okay. So again, very close to what was expected. Okay, and this will be the case no matter what your sample size is. We did 4 and 10, doesn't matter. The mean of your sample means should theoretically equal the mean of the population. But then, like we talked about the other night, there were some differences in the distributions. Okay, I'm going to erase this stuff and go on to the next page. Okay. All right, so the main difference that we saw was kind of the spread of the sampling distributions as we went from a sample size of 4 to a sample size of 10. We saw that the distribution here was tighter and less spread out. Okay, and you know, we know what that means in terms of standard deviation. This standard deviation is smaller than this standard deviation, and they're both less than the population standard deviation. Okay, so in other words, up here, the standard deviation of the sample means gets smaller as the sample size gets larger. Okay, so in symbols, we would write it like this: the standard deviation of the sample means, which would be sigma sub x bar, is equal to the standard deviation of the population, sigma, divided by the square root of the sample size, n. So again, sigma is the standard deviation of the population. All right, so let's go back and test this with our experiment. For the population data, you 32 students, your ages, the population standard deviation that I calculated in StatDisk was 7.983. All right, so that's the standard deviation of the population. All right, so for the sample size of 4 then, theoretically, the standard deviation of this distribution should equal sigma divided by the square root of the sample size 4, okay? So in other words, it should equal 7.983 divided by the square root of 4, which of course is 2. And if you go ahead and calculate that, you should find that sigma sub x bar theoretically should equal about 3.992. Okay, that's what it should equal. And again, that would be if you had taken all possible samples. Of course, we didn't. We only took 60. So from our actual results, all of the means that you guys calculated when I typed them in, the actual standard deviation was 4.317. All right, so this about 4, this about 4.3, pretty close. All right, for the larger sample size of 10, theoretically, the standard deviation should equal sigma divided by the square root of 10. All right. So in other words, I'm not going to write this out, but you can. It should equal 7.983 divided by the square root of 10. And if you calculate that, you should get about 2.524. All right, theoretically. When I took all these sample means, typed them in, found the standard deviation, it was about 2.944. All right, so again, about 2.5, about 2.9. Okay, reasonably close for our relatively small number of trials, which was 60 total. Okay, so again, to summarize some important points about the sampling size and the variability, I'm going to erase this stuff and scooch down if you want to pause for a second. Okay. All right, so again, this value sigma sub x bar, it is the standard deviation of the sample means. Okay, it is the standard deviation associated with the sampling distribution, as opposed to the standard deviation of the original population. That's just plain old sigma. It is going to be less than the standard deviation of the original population because the sample means in general have less variability in them than the original data. Okay, just doesn't vary as much. It is also called the standard error of the mean, just in case you see that term in the book, the standard error of the mean. And the important point is that it gets smaller as the sample size gets larger. I mean, we saw this even before we calculated it or knew what it was supposed to be. We saw that this sigma was smaller than this sigma. Okay. All right, I'm going to go on to the next page. Okay. And there's really just one more concept in this section, which is looking at the difference between a variable which is normally distributed and a variable that is not normally distributed. Now, if you remember from the video we watched, with the little kids and their heights, their population distribution was normal, okay? Now, the example we did, your ages, that was not normal, okay? So our population distribution right here was very right skewed. Okay. And when we did our sampling distributions, we saw that n equals 4, still pretty right skewed. N equals 10, still a little right skewed, but getting much closer to being bell-shaped. And this actually demonstrated pretty well an important theorem in statistics, which is called the central limit theorem, which says for a relatively large sample size, and we'll define that more clearly, the variable x bar, the sample means, is approximately normally distributed, regardless of the distribution of the variable. The approximation to a normal curve becomes better with increasing sample size. Okay. And generally, the rule of thumb for what a relatively large sample size means is a sample size that is greater than or equal to 30. Okay. And that is a very conservative assumption. I mean, you can see that with our experiment. We only did a sample size of 10, that was our larger one, and still our distribution came out almost bell-shaped. Okay, not quite, but almost. Now, if the variable is normally distributed to begin with, then any sample size will provide a normal distribution for the sample means. And we saw that in the video with the kids and their heights. Their population was normal to begin with, okay? And they took samples of size 4. And even though that was a very small sample size, their sampling distribution came out normally because the population was normal to start with. All right? Our population was very skewed. Therefore, with a smaller sample size, our sample distribution is still skewed. All right? Okay, I'm going to erase and go on to the next page. So here's a good figure. I think it's not from our textbook, but I really like this figure because it just gives you a better idea of what they're talking about here. So this top row is showing the distribution of the variable. In other words, the population distribution. So maybe you start with a population that is normally distributed, like the kids and their heights. Maybe you have a very skewed distribution, like our ages, like the class ages. Or maybe you start with the uniform distribution. These are just the 3 examples, okay? And then what it shows here is different possible sample sizes that you might take, calculate the mean, plot the sampling distribution. So as you can see, with the normal population to start with, it doesn't matter how small your sample size is. Your sampling distribution is always going to be perfectly normal and bell-shaped. If your distribution is right skewed to start with, then with a small sample size, you're still going to have a skewed sampling distribution. And that is exactly what we saw. N equals 10, exactly what we saw. Still a little bit skewed, but getting close. Large enough sample, 30, your sampling distribution is going to be nice and normal and bell-shaped, okay? And the other thing this figure shows is that regardless of the sample size, that all of your sampling distributions are always going to have their mean located exactly where the mean of the population is. All right. All right, I'm going to erase and go on to the next page. All right, so here just to summarize kind of these important points that we just covered. So we've got some variable, in our case it was ages, it has some mean and some standard deviation associated with that population. You're going to take samples of size n, you're going to calculate the mean for each sample, okay? So for these samples of this particular size n, the mean of the sample means, mu sub x bar, is going to equal the mean of the population, mu. The standard deviation of the sample means is going to equal the standard deviation of the population divided by the square root of the sample size. Okay. If the population variable is normally distributed, then the sample means will also be normally distributed regardless of the sample size. Okay, so there's no restriction on the sample size n. If the population is not normally distributed, like the case we did, still the sample means will be approximately normal if the sample size is large enough, and specifically what we mean by that is if n is greater than or equal to 30. Approximately. And again, that's a fairly conservative assumption. All right. So how we're going to use this then, using the central limit theorem in calculations, it allows us to calculate probabilities or percentages for certain sample sizes or groups, okay? Instead of just calculating probabilities for individual or single values. All right? Okay, I'm going to erase and go on to the next page. We'll do an example. All right, so let's look at an example. If you remember, last chapter, we had done a particular problem. We calculated the probability of randomly selecting a single woman and having her height be less than 5 feet. Okay, given that the population is normal with a mean of 63.8 and a standard deviation of 2.6. So we took the individual data value, 5 feet or 60 inches. We converted it to a z-score just by doing z equals x minus mu over sigma. So we did 60 minus 63.8 divided by 2.6. We found that the z-score was negative 1.46. Okay. And then we went to the table and we looked up a z-score of negative 1.46, and the area to the left of that is 0.0721. Okay, so in other words, about a 7% chance that a randomly selected woman will be less than 5 feet tall. Okay, so now we want to ask a new question, which is, if a group of 10 women is randomly selected, find the probability that their mean height is less than 5 feet. Okay, so before we do anything, just intuitively, what do you expect? How do you expect this probability to compare to this probability? One woman, height less than 5 feet, about 7% chance. 10 women, measure them all, calculate the mean height. What's the probability that that mean height is less than 5 feet? What do you think? And if you're, thinking about it, kind of remember from the video what that lady was saying about how, the means are going to tend to be closer to the actual mean of the distribution. Because if I reach into the bag and I pull out 10 women, I might get a couple that are short, I might get a couple that are tall, I might get a bunch that are closer to the middle. And if I calculate the mean of all that, I think the chances of that mean being less than 5 feet is going to be very, very small. Because for that to happen, I would have to get almost all of the 10 women to be very short. And that's probably not going to happen, right? So anyway, we'll come back and do that actual calculation in a second. But we want to start by just describing the sampling distribution of the means for sample sizes of 10. Okay? And this is just, kind of using the wording from the book Problems. So it's 3 things. When it says describe the sampling distribution, there's these 3 things specifically that it is asking for. What is the shape of the distribution going to be? Well, in this case, it tells us the population is normal. So therefore, even though the sample size is small, the sampling distribution is also going to be normal. So the shape of the distribution will be normal. Find the mean of the sampling distribution, the value in the center. Well, we know that that is just going to equal the mean of the population, which was given above. So mu sub x bar is going to equal 63.8. Okay, same as the population. And then find the standard deviation of the sampling distribution. Okay, and we just learned that this is going to equal standard deviation of the population divided by the square root of the sample size. Okay, so this is going to be sigma is 2.6, and then divided by the square root of the sample size is 10. And if you calculate that, you should get about 0.82219. All right, so that's basically what they mean in the book when they say describe the sampling distribution. Okay, now that we've done that, we can go back and actually calculate the probability. Okay, so we're just dealing with the normal distribution here. I'm just going to draw another distribution over here. Okay, this is my sampling distribution of the means for a sample size n equals 10. We know the value in the middle is mu sub x bar is 63.8. The data value in question here is still 5 feet. And again, 5 feet times 12 inches per foot is 60 inches. So somewhere over here, just mark that, there's 60. The probability that the mean height is less than that. Okay, so again, we're looking for the area to the left of that data value. And as before, what we need to do is calculate the z-score that corresponds to that data value. All right, but the difference here in the formula that we use for the z-score is that we do z equals the data value, minus, in this case, mu sub x bar, okay, and then divided by sigma sub x bar. All right, so we need to use the mean and standard deviation that correspond to the sampling distribution, not the population, because we are dealing with a sample size of 10. All right. Now, of course, the mean is the same, so it's still just, data value x is 60, and then I want to go minus the mean, 63.8. But now in the denominator is where the change comes, because we need to divide by this. In other words, 2.6 divided by the square root of 10. All right. And as you do that on your calculator, you know, it's best to just do this all at once, okay? So when you type this in, you're going to want to put parens around your numerator. So paren, this minus this, end paren, divided by, and then another paren here, 2.6 divided by the square root of 10. And I know for a lot of you, even when you do a square root, then there's a paren at the start, and then you got to put a paren at the end. Now you got to put another one out here to end the denominator. All right, just give it a try on your calculator. Make sure that you know how to do that. And what you should come up with is a z-score of negative 4.62. All right. So in other words, this data value with the sample size corresponds to a z-score of negative 4.62, which, you know, as you know, is way off to the left, and it's off the end of the chart, which means that there's such a teeny tiny bit of area that, according to our book, we would report it as less than 0.0001. Approximately 0, but remember, it's not exactly 0%. But in other words, there is an extremely minuscule probability that that would happen, which again makes sense. Okay. And one student described it as, again, if you've got all the women in a bag and you're going to start grabbing them out, it's easier to grab one freak, no offense to anyone, out of a bag, as in one very tall person or one very short person, but you're probably not going to grab 10 freaks out of a bag, 10 extremely short people, short to where their mean height would be less than 5 feet. Okay. All right, I'm going to erase and go on to the next page if you want to pause this. All right, so what I would like is, whoops, to get back to where I meant to be, here, is for you to pause the recording for a minute and try this problem on your own, okay? This is basically just like what I ran through on the previous page. We've got a normal population of test scores. Here's the mean, here's the standard deviation. And just a comment that for question A, you're only selecting one man, all right? You don't need to use the central limit theorem here. This is just back to plain old chapter 7 stuff. Just calculate the z-score the normal way. Question B, again, it's asking you to describe the sampling distribution. Those are just the 3 items on the previous page that I told you. And then part C is where you're getting down to using the central limit theorem, because now you're going to grab 16 of the men and find their mean test score. Okay? All right, so pause, take a look at this, and then I'll come back and go over the answers. All right, so let me go ahead and run over this problem. Again, this is we're dealing with a normal population. Here's the mean, here's the standard deviation. If one man is randomly selected, find the probability that his score is at least 590. And of course, you should know that means 590 or more. So in other words, if I just draw a normal curve representing the population, okay, and so right in the middle is the mean, which is 509. The data value that is in question is 590, so that's just up here somewhere. Doesn't really matter where. 590, and we want the probability or the area to the right of that data value. Okay, so just like we did in chapter 7, just calculate the z-score. So x minus mu. All right, so 590 minus 509, and then divided by sigma, which is 112. All right, so you should find that z-score is 0.72. Go to the table, and you should find the area to the left of that z-score is 0.7642. And what we really want is the area to the right. So just do 1 minus this value, and we find that 0.23, oops, sorry, I totally screwed that up, 0.2358. All right, so that's the probability that goes here, about 0.2358, about 24% chance that somebody gets, like 590 or more. All right, describe the sampling distribution for samples of size 16. Like I said, there's 3 items here. First of all, the shape of the distribution. Well, the population is normally distributed. Therefore, the sampling distribution, no matter the sample size, is also going to be normally distributed. So that's the shape. Okay. The second item is the mean. All right. And the mean of the sampling distribution is just going to equal the mean of the population, which is 509. And then the standard deviation of the sampling distribution is going to equal the standard deviation of the population, which is 112, and then divided by the square root of the sample size, which is 16. So again, these numbers are going to work out nice because 112 divided by 4 is 28. All right, so sigma sub x bar is exactly 28. If 16 are randomly selected, find the probability that their mean score is at least 590. So they're asking about the same data value, but the distribution is different because it's the sampling distribution, which means it's going to be taller and skinnier. It's still going to be centered at the same value, 509. And we still have the same data value, 590. All right, and we still want to find that same area above 590. But this time when we calculate the z-score, we're doing it relative to the sampling distribution. All right, so I'm going to do z equals x, 590, minus mu sub x bar, which is still 509, and then divided by sigma sub x bar, which is this. And I know it's 28. I'm just going to go ahead and put, the actual original numbers in here, like this. And again, just if you want to practice and make sure you're doing this right on your calculator, do the parens, all right. And so you should get a z-score of, I got 2.89. All right. So that corresponds to here, z equals 2.89. Go to the table, look up the area to the left of 2.89, and you should find that that is 0.9981. Sorry, my pencil work is terrible here, but that should say 0.9981. We want the area to the right, so do 1 minus that, and and we get 0.0019. Okay. So the probability of selecting 6 of the men and having their mean score be above 590 is 0.0019, which is, less than 1%. So is that unusual? Yes, definitely, because clearly this is much less than the 5% threshold. So yes, it is unusual. Okay. All right, and then the last question, there is a 10% probability that the mean score of a random sample will exceed what value? All right, so this is, the reverse problem. This is, you're given the area, you want to calculate the data value. But again, this is being done relative to the sampling distribution. So let me draw one more curve down here. Okay, and again, this is supposed to be representing the sampling distribution. So I've still got the same mean right here in the middle, 509. All right. 10% chance. So in other words, I want for there to be 10% area. All right, in this tail of the curve. And I want to find out, sorry, that's not what I meant to write. I meant to write x equals what? What data value has 10% of the area above it? Well, if it's got 10% of the area above, then it's got 90% of the area below. So you do this first part exactly the way that we would have done it before, back in chapter 7. Go to the table, look in the body of the table to find what z-score has an area of 0.90 to its left. So pause for a sec and go to the table, and obviously you're going to be on the positive side. Find the number in the body of the table that is closest to 0.90. All right. Okay, and what you should find is that the corresponding z-score is 1.28. All right, so make sure that you see how to do that. All right, so the z-score is 1.28. And now we're just going to do exactly the same thing we did back in chapter 7. If you remember the formula, x equals mu plus z sigma. All right, except this time we're going to do equals mu sub x bar plus z sigma sub x bar. Okay. So in other words, the data value that we're looking for is equal to the mean, which is 509, and then plus the z-score, which is 1.28, times the standard deviation of the sampling distribution. Okay, again, that's sigma sub x bar. All right, so I'm just going to go ahead and put in 28. So we already calculated that. All right, and if you calculate that out, you should get about, I got 544.84. Or you could say, approximately 545. Okay. 10% chance that the mean score of 16 will exceed this value. All right, I'm going to pause for a sec before I go on to the next section. All right, so let's go on to section 8.2, where we're just going to basically extend our discussion of sampling distributions now and talk about proportions. Okay, so instead of the sampling distribution of the mean, we're going to talk about the sampling distribution of the proportion. And we haven't worked with proportions as much as we have with means. It's basically just the ratio or percentage of a population that has some characteristic that you're looking for. So there's nothing complicated about proportions. They're actually even easier to work with. Just as an easy example, the proportion of guys in our class out of the people we have in the class now is we have 5 guys out of 29 total students. So if you just divide that out, the proportion is about 0.172 to 3 significant figures. Okay. The thing is that it's a different type of data, proportions are. So for example, with your ages, which is what we were working with before, that is discrete quantitative data. Okay, discrete quantitative, you know, numerical. So when I had the list of everyone's age in the class, I can calculate stuff like the mean or the median or the standard deviation or any other number of things. Versus something like the proportion of males, or something like another question I asked you was, do you have a tattoo? Yes or no. Okay. For either of those, the data is qualitative or categorical data. It's non-numeric. You know, it's basically either yes or no. Yes, I'm a guy. No, I'm not. Yes, I have a tattoo. No, I don't. So I just have a list of yeses or nos. I can't calculate the mean or the standard deviation of that. But what I can calculate is the proportion of responses that were a yes or a no. So looking at the tattoo data, the number of responses, now why do I only have 29 here? I feel like I should have more. Yeah, let's just go with it. My sample size was 29. The number of successes, X, was 12, where a success is somebody that said, yes, I have a tattoo. So from that, I can also calculate the sample proportion, and we use lowercase p hat to indicate a sample proportion. So that's 12 successes out of a sample size of 29. 12 divided by 29 to 3 significant figures, 0.414. Rats. 0.414, sorry. Okay, so the thing is, you know, if we considered this to be a random sample, even though it really wasn't, but it was a sample of 29, if I were to go out and take another random sample of another 29 CBC students, would I get exactly that same sample proportion of students that have a tattoo? Probably not. Okay, I would probably get a different sample proportion because samples vary. Okay, every sample you're talking to different people, you're probably going to get different answers. So if I did this a whole bunch of times and got a whole bunch of different samples of 29 students, then I would have a whole bunch of different sample proportions. And if I plotted those, that would be a probability distribution. Okay, so kind of just like we saw for the means, we can do exactly the same thing with proportions. Okay, I'm going to erase this and go on to the next page. So we are going to look at something, a particular example, using the candy Reese's Pieces. All right. And we're in particular going to look at the proportion of them that are orange. Now, according to the manufacturer, they have 50% orange candies. So you know what Reese's Pieces are, right? Reese's Pieces. They look like M&Ms, but they're nasty tasting. So half of them are orange, and then there's also yellow and brown, and that's it. So the proportion we're interested in are the orange. So in other words, our population proportion of orange is 0.5, and therefore 1 minus that, because we're going to need this number too, also happens to be 0.5. So if we wanted to look at a plot of the population, again, this is just a different type of data, we would basically, this is categorical data. Either they're orange or they're not orange. 50% are orange, 50% are not orange. Okay? Now, what I normally do in the class is we actually do an experiment where I count out, and I calculated this, a total of 1,500 candies so that I can make 2 baggies of 25 candies for each student. So that's a total of 60 baggies times 25. Let me just make sure I'm doing that math right. Yeah, 1,500 candies. So I'm actually kind of glad I'm just doing this on a video, so I don't have to count out all the candies. So anyway, the point is everybody gets their 2 baggies, and each baggie has 25 candies in it. And then your sample proportion for each of the 2 baggies is how many orange candies out of the total number, which is 25. Now, knowing that 50% by definition are orange, you would expect about half of the candies in your baggie to be orange, right? Well, you can't have exactly half of 25. That would be 12.5. So maybe you would think, well, I would expect to get about 12 or 13 orange candies in each of my bags. But again, samples vary. So yeah, these are very possible, but it's also possible maybe you have 11 or 14 or 10 or 15 or etc. There's going to be a distribution, right? All right, I'm going to pause and go on to the next page. All right, so since we're not able to actually do the live candy experiment, instead I'm going to do this online applet, which I am sure is where I had originally gotten the motivation to do the experiment in the first place. This Rossman and Chance are authors. They've written a wonderful series of statistic workbooks that I get a lot of my material from. So I'm sure that I had seen this in the past, and this is why I do this. So Reese's Pieces, we know that the probability of orange is 0.5. I'm going to leave the number of candies at 25. We're going to start by just doing one sample at a time. And down here, I can display either the number of orange out of the 25 or the proportion of orange out of 25. And again, we already, said knowing that the proportion is 0.5, exactly in the middle would be 12.5, but we can't get that. So 12 would correspond to a proportion of like 0.48. 13 would be 0.52. So let's just do a sample and see what happens. All right, 0.52. That would be 13 orange candies. Totally expected, right? Okay, let's do another one. 0.48. All right, so we're basically bracketing the expected center value. Let's do another one. Okay, not as many orange in this one, so the proportion was only 0.32. Let's do another. 0.48. Okay, let's do another. All right, 0.48 again. Okay, so let's kind of up the ante this time. Instead of doing one sample at a time, let's do 50. Now it's just going to animate one, but then it's going to pop all of them onto the graph. So don't worry, we're not going to have to sit here while it does 50 samples. So let's go ahead and do that. I think I just hit the button twice by accident. Yeah, because we just ended up with a total of 105, which is not really what I meant to do, but that's okay. Let's just go with it. So, okay, all of a sudden you can see what our curve is starting to look like. And again, the middle is like right here, right in between 0.48 and 0.52. All right, let me hit it one more time. I'm just going to try to do it once this time to add 50 more, and we'll see what happens. Okay, wow, this turned out well. So as you can see, this is basically, you know, and these are all out of, we've now got a total of 155 samples, which is a lot more than we would have done in class. In class, we would have only had 60. Now we've got 155, but you can see exactly what has happened here is we've basically got a very bell-shaped normal distribution of the sample proportions. So, and the center, you know, again, the center is kind of exactly here. And you can kind of see that's about where the bell-shaped curve is centered. So had we done this in class, you know, the center would be about here, and you could have anticipated kind of a bell-shaped curve right over the center. Okay. All right, I'm going to erase this stuff and move on to the next page. So again, notice that the shape of the distribution of the sample proportions, again, that's basically this, is approximately normal. Notice that the mean of the distribution of the sample proportions, and again, you know, it kind of looks like it's somewhere right in here, okay, is approximately equal to the population proportion P. Okay, so just lowercase p stands for the population proportion. If we had done this for different sample sizes, we only did it, each sample of candy was 25. If we had also done the simulation, say with a smaller sample size, then you would notice exactly the same thing as we saw with the sampling distribution of the means, which is that the standard deviation of the sample proportions gets smaller as the sample sizes increases. Okay, and again, we saw that with the distribution of the sample means. So for example, if we had done n equals 5, maybe the sample proportions would look like this, versus what we just did with n equals 25. Relatively, it would be more like this. Okay, less standard deviation. All right, so kind of a summary of the sampling distribution of the sample proportions. Again, that's what p hat is, the sample proportion. For a simple random sample of size n with a given population proportion p, the shape of the sampling distribution of p hat is approximately normal, provided that n times p times 1 minus p is greater than or equal to 10. Okay. Now this, we've seen this before. This is basically saying it's just a requirement that the sample size is large enough. All right. Let me scoot this off so I can write off to the side here. Now technically, for what we just did for the Reese's, the sample size is not really big enough, because if I were to calculate this quantity for the simulation that we just did, n, our sample size was 25, p, proportion of orange, was 0.5, 1 minus p, also 0.5. Okay. And if you calculate all that out, you get 6.25. All right, now 6.25 is not greater than or equal to 10. So technically, we should have had a bigger sample size than 25. On the other hand, as you can see, our results were, in fact, pretty darn normal, right? So again, when we use that requirement, that is a very conservative requirement. Okay? All right, and back to this. The mean of the sampling distribution of the sample proportions is, I'm just going to write this off to the side so I can write it nice and big. Mu mean sub p hat, the mean of the sample proportions, is equal to p, okay, the actual proportion, actual population proportion, okay, and the standard deviation of the sampling distribution of the sample proportions is, again, I'm going to write this off to the side so I can do it nice and big, sigma sub p hat is equal to the square root of the quantity p times 1 minus p divided by n. All right, where p is the population proportion, n is the trial size. Okay. Now for this in particular, just proving this or deriving it is out of the scope of what we're doing here, but generally it is based on the binomial distribution, because any proportion is basically binomial. In this case, either the candy was orange or it wasn't. Or in the case of your tattoos, either you have a tattoo or you don't. Okay? So that's where this stuff is derived from. And then finally, down here at the bottom, one more requirement of using this model is that samples have to be independent of each other. And if you're sampling from a finite population, just a certain size, you need to verify your independence by checking that your sample size is no more than 5% of the population size. So in other words, we need our sample size, lowercase n, to be less than or equal to 0.05 capital N, where capital N is the population size. Now, in the case of the Reese's Pieces, it's really not a finite population. There are infinitely many candies available. If we eat them all, they're going to make more, right? So I'll kind of show you an example of this on the next page. All right, I'm going to pause, go on to the next page to do an example. Okay, so let's look at an example now of how we will use this. So let's see, according to a recent, this month, study done by Gallup, the proportion of U.S. adults who support amending the Constitution so that the winner of the popular vote would win the presidential election instead of using the electoral college system is 0.55 or 55%. All right, so in other words, this is our population proportion, P. Okay. All right, so suppose a random sample of 100 adults is asked. Do you support amending the Constitution rather than keeping the current electoral college system? Is the response to this qualitative or quantitative? Well, of course, it's qualitative. It's a yes-no question, so the answer is qualitative or categorical. Explain why the sample proportion p hat is a random variable. What is the source of the variability? And again, just samples vary. If you went out and asked 100 people the question, you're going to get one proportion. If you go take another sample of a different 100 people, you're probably going to get a different answer. You will get a different sample proportion because you're talking to different people each time. C, verify the model requirements, describe the sampling distribution of p hat. So we need to verify, is the sample size less than 5% of the population size? Okay, so first of all, the sample size was given up here, 100. So that's our sample size, lowercase n. Now, the population size in this case would be the entire population of U.S. adults, which is many, many millions, 200 plus million U.S. adults. So yeah, we don't even need to calculate that. We can just kind of check that off the list. 100 is very small compared to the population size. Verify that our sample size is large enough. All right, so in this case, we do actually want to do this calculation. I'm going to come up here to the side. So N is 100. P, population proportion, is 0.55. And then times 1 minus P, 1 minus 0.55 is 0.45. All right, so if you do that calculation, 100 times 0.55 times 0.45 should get 24.75, which obviously is, oh, sorry, I'm gonna sneeze. Excuse me, is greater than or equal to 10, so that tells us, yes, the sample size is big enough. All right, and then describe the shape, the mean, and the standard deviation. Just warning, I might sneeze again. So, because we have, verified these two, then we know that the shape is going to be approximately normal. We know that the mean, the mean of the sample proportions, or mu sub p hat, is going to equal p, the population proportion, which is 0.55. Okay. And to calculate the standard deviation of the sampling distribution, again, I'm going to come off to the side here so I have more room. Using the formula from the previous page, sigma sub p hat is, let me just write the formula out again, the square root of p times 1 minus p divided by n. All right, so that's going to be the square root of, and again, p is 0.55. 1 minus that is 0.45. And we're dividing by the sample size, which was 100. All right, and if you calculate all that, make sure you're doing this correctly on your calculator. You should be able to do that all at once, which when you're doing that on your calculator, then you probably want to do a double set of parens under the square root. Okay. And you should get about 0.04975. Okay. Okay, and then on to question D. In a random sample of 100 U.S. adults, what is the probability that the proportion who support amending the Constitution is greater than 0.60? All right, well, let's just draw a curve. Okay, and at the center is the population proportion, because that's what mu sub p hat equals. So this is 0.55. And then the data value in question is the proportion 0.60. All right, so that's obviously up here somewhere. 0.60. We want the probability that it's greater than that. So in other words, we want the area above it. That's what we want to find. So in order to find that, we need to calculate the z-score that corresponds to this data value. Okay? So in this case, we calculate z. All right, we've been doing x minus mu. So our x, our data value in this case, is our sample proportion, p hat, minus mu, in this case, is mu sub p hat, the mean of the sample proportion, which also equals p, and then divided by sigma, which in this case is sigma sub p hat. And we know all of these numbers. Our sample proportion is 0.6. Our mean is 0.55. And we just calculated our standard deviation, which was 0.04975. All right. So if you calculate that z-score out, should get 1.01 rounded off correctly to 2 decimal places. Okay. So this corresponds to a z-score of 1.01. Go to the table, look up the area to the left of a z-score of 1.01, and you should find that it is 0.8438. What the problem asks for is the area above that. So we just need to do 1 minus 0.8438, which would be 0.1562. Okay, so that's the probability that we are looking for. P equals 0.1562. All right, last question, E. Would it be unusual for a sample of 100 to reveal that 40 or fewer? Now, in this case, it didn't give us the sample proportion. This one gave us the sample proportion, 0.6. Here, we have to calculate it. So the actual sample proportion in question is 40 out of the sample size, which was 100. So it actually is going to be exactly 0.4. That's just because the sample size happened to be 100. All right, so now we're looking at exactly the same type of problem. So let's just set up another curve. All right, so again, we've got 0.55 right in the middle. Now the sample proportion in question is 0.4. That's down here somewhere. And we want to know 40 or fewer. So in this case, we're trying to find this area to the left of 0.4. Okay, so we got to calculate the z-score corresponding to 0.4. It's exactly the same as this calculation here, except that we're going to substitute in 0.4. So I'm going to do 0.4 minus 0.55 over sigma sub p hat, which again 0.04975. All right, and that you should find equals negative 3.02. Right, go to the table, look up a z-score of negative 3.02, and you should find that this area is 0.0013. So that is the probability that we're looking for. All right, so the probability of that happening is 0.0013. Would that be unusual? Yes, it would be unusual because this number is definitely less, sorry, that's a less than symbol, less than the 5% threshold. So yes, that would be unusual. All right, so what I want you to do is pause this, go on to the problem on the next page and give that one a shot by yourself first, and then I'll come back and show you the solutions. Okay, let me run through the solutions to this problem. According to a recent report from Pew, also this month, the proportion of Americans in favor of allowing gays and lesbians to marry legally is 61%. All right, so in this case, this is our population proportion, P, 0.61 in decimal form. Suppose a random sample of 120 Americans, all right, so there's our sample size N, is asked whether or not they favor allowing gays and lesbians to marry legally. Verify the model requirements, describe the sampling distribution of p hat. All right, so same deal here. Is the sample size 120, less than 5% of the population of all US adults? Yes. Verify that the sample size is large enough. All right, so we just need to calculate N, which is 120, times P, which is 0.61, times 1 minus P. 1 minus 0.61 is going to be 0.39. All right, and if you calculate that, you get 28.548, which is greater than or equal to 10, which indicates that yes, our sample size is big enough to use this method. The shape of the sampling distribution of proportions is going to be approximately normal then. The mean mu sub p hat is going to just equal p, the population proportion, which is 0.61. And the standard deviation, sigma sub p hat, we're going to use the same formula. It's the square root of p times quantity 1 minus p divided by n. All right, so p, again, 0.61. 1 minus that is 0.39. And the sample size n is 120. All right, and if you calculate that, should get about 0.05 44525. You know, in general, on this calculation, just keep more digits than you would think. Don't round it off to 0.04 or even 0.045. Just keep a few extra digits. Otherwise, you're going to lose accuracy when you use this number in the next step to calculate your z-score. All right, B. In a random sample of 120, what is the probability that the proportion who favor is greater than 0.65? All right, so that's the data value in question. Let me come over here and draw a normal curve because our sampling distribution is normal. Right at the middle is P, which is 0.61. All right, the sample proportion in question is 0.65, which is somewhere to the right of here. Let's just draw it up here. We want to know the probability that it's greater than that. All right, so we want to know this area. So to find that, we need to calculate the z-score associated with this data value of 0.65. All right, so let's come down here and calculate the z-score, which is equal to the data value, all right, the sample proportion, which is 0.65, minus the center value, mu sub p hat, which is p, and then divided by the standard deviation of the sampling distribution. All right, so p hat, 0.65, and then subtract the mean, which again is just the population proportion of 0.61, and then divide by that standard deviation that we just calculated up here, 0.044525. All right, and if you calculate that, you should get a z-score of 0.90. All right, so this data value corresponds to a z-score of 0.90. Go to the table, look up your z-score of 0.90. That will tell you the area to the left, which is 0.8159. And what we want, what the problem asked for, is the proportion greater than that. So we want this, so we just do 1 minus 0.8159, which is 0.1841. All right, so that's our answer. That is the proportion, 0.1841, so about 18%. Okay. All right, question C, would it be unusual to reveal that 60 or fewer are in favor? All right, so again, in this case, we have to calculate our sample proportion. All right, our sample proportion is the number of successes over the total sample size. So we're talking about 60 out of 120. All right, so that's just half, or 0.5. So that is the data value in question here, sample proportion of 0.5. All right, draw a normal curve. Okay, again, right in the middle is P, or mu sub p hat, 0.61. Now we're asking about 0.5, so that's to the left, 0.5. 60 or fewer, so that indicates that we want this area to the left. That's what we're trying to find. Okay, we have to convert this data value to a z-score using exactly the same method that we just did for part B, except instead of 0.65, we're calculating for 0.5. So z is 0.5 minus the mean, which is 0.61, divided by the standard deviation, okay, 0.044525. All right, and if you calculate that, should find that it equals negative 2.47. Okay. Go to the table, look up a z-score of negative 2.47. You should find that the area to the left of that is 0.0068. Okay. And then the question was, would that be unusual? Well, again, that's a very, very small probability. It's less than the threshold of 5%. It's less than 0.05. So in other words, yes, it would be unusual if that were the case because the probability is very small, less than 5%. Okay. All right, so I'm going to go ahead and just stop this recording and then start a separate one to start into section 9.1. I just don't want to let this one get too long because it takes too long to upload. So